Okay, and in this presentation, this is not intended to be a lecture. I'm not going to focus too much on the actual results. I'm going to introduce to the entire concept of characterization work, which GSQ Minerals have been doing for the past 5-6 years. A large body of work happening in that area. And I'm going to give you a brief introduction of the purpose, the intent, why we're doing it, some teasers, some main results which you can easily get out of the data. The main focus, and that's for you to keep in mind, is to try and figure out how this data, how these results can relate to what you do on the ground, because the main point of this exercise is to try and help people doing exploration. And that's a very valuable thing for us to get as your feedback, how useful or not you find this exercise to be, and how you want us to do it better, and to do different kinds of work, expand something, to do less of something. After this presentation, Elena will go into some details of some more advanced analytical techniques. So I'm going to touch on them, and Elena will dive quite deeply into them. Some techniques which are quite often not used in exploration and mining, usually the realm of the academic world, and we're going to show you about how they can be and are employed to help in exploration. And then after lunch, we're going to do core viewing in the core store, and that's one of the outputs, one of the target outputs of this whole exercise, of collecting reference collection of materials, collecting representative drill cores from all key deposits, and making it available to everybody as a public resource to view, to touch, and to do some more advanced work, and to feed that for academics and for industry for years to come. And at some point it will do something. I guess it's going. It's not synchronizing. Okay. Okay, I'll have to check so what's happening behind my back. So the logic of this entire exercise of deposit and mineral system characterization is to characterize what's happening inside deposits, what happens in the inalteration zones, and focusing on characterization in mineralization, what's in the ore, what is the geochemical mineralogical signature of ore, what is the mineralogical and geochemical signature of proximal alteration. In recent years, it became very topical to pay close attention to critical minerals. And in Northwest Queensland in particular, and in general, lots of critical minerals are present as potential byproducts, and quite often the ones which companies don't normally analyze. And stepping out of the deposits, the task is to accumulate representative collection of samples and data to assess deposits footprints, distal deposit footprints, for extent into distal mineral system footprints. And that's pretty much the end game of this entire exercise. We're doing most of our deposit scale data acquisition as a starting point to step out and to get a good guide to how to interpret exploration results in the middle of nowhere. So when you get a 1 centimeter thick chalcopyrite vein, to give you some confidence to associate it with a certain mineral system type or certain deposit type, a certain age, and provide vectors towards mineralization. So keep in mind that even though mostly we're talking about what happens within deposits on their close outskirts, the end game is pretty much this: how to help you to recognize distal footprints of alteration, how to give you confidence to continue exploring, and give you indications where to go. So this work, in earnest, we started in 2019, so it's been about 5 years. So far, so we've done some work on more than 70 deposits. So to give you a scale, so we focused mostly on Northwest, Northeast, because these are the premium mineral provinces, starting from Northwest, expanding to Northeast. But we start doing more work in Central and Southern Queensland. And the amount of work with was pretty staggering, and outputs quite often are lagging behind just because we're busy collecting the data. So that's been the focus. And even though the work is done mineral system by mineral system, deposit by deposit, so the end result is trying to characterize, what is the feel, what are the properties of the Cloncurry district of ICGs, what are the properties of sediment-hosted copper deposits in Western Mount Isa. So that's the main approach. And the key point of the exercise is to acquire representative collection of drill cores, and that's where we cannot possibly do it without help of the industry, and the help was pretty overwhelming. So that's thank you all. Without this help, without your coordination and sharing your knowledge about the drill core in their context, we wouldn't be able to do any of this work. So as a routine workflow, one part of the exercise was to make sure that we collect data of the same kind in comparable parameters to allow easy comparison between deposits. So that was one key gap. So when we started this, there were some deposits which were studied by multiple PhD students over decades, and some deposits which were barely touched by anything. And the good results, which were commonly using as a start when we have a luxury, is deposit atlases. So that gives us a good context to start active selection of drill cores, or to place existing drill cores which we have in our possession in the deposit context. Routinely, when we get the drill core, select the representative ones, we do hold the drill core scanning. We have our very own halogen machine, so it gives us a very good assessment of the mineralogy downhole. So we do campaigns of other instruments like Mineralizer, TrueScan, continuous XRF, and we proceed with on the basis of core logging by spectral and XRF scanning machines. We do sampling. So when we understand the context of the drill core, and so all the work from that point onwards starts on individual samples. And suppose the point of the sampling is to provide a representative set of samples and then data to represent variability, the average and the variability of the properties, immunization, and alteration. So that's to refer to the point of representativeness. How do you select a representative sample to represent a major deposit? Well, the simple answer, you can't. You have to select multiple samples, and that's what we do. So we're selecting tens to hundreds of samples within a deposit to be sure that we do capture the actual properties of mineralization and alteration. And from the point of sampling, we do a fair bit of geochemistry. And again, the point of the exercise is standardization. So we're using the same techniques widely used in the industry to make sure that the industry data can be directly comparable to ours. So but we're using the same commercial labs and the same standard tools, standard methods that are used by the industry, so that you are not limited to just our outputs. You can easily plug in your data and find your way around using our data sets as pretty much as a skeleton. And on the basis of geochemical results, so we do some more advanced characterization using the vast array of advanced analytical techniques, and Elena will talk more about those. Yep. Okay. Okay, thank you. Good. Well, that's fine. So it's my fault. So I'm trying to go through 48 slides in 40 minutes. That's going to be hard. Okay. Okay, in that case, when I run out of time or run out of time, Elena will forgive me. Okay. So we have done a fair bit of work in Northwest and Northeast because where we are, I'm not going to say anything at all about Northeast. So we had some discussion in Charter's House not so long ago, and when we take this roadshow to the east, there we'll focus on the Northeast. So we did work by mineral system type. So we're not focusing so much on specific boxes, specific classification categories of deposit types. So we're going by mineral systems, and the major ones in this part of the world are IOCGs and affiliated deposits. so-called sediment-hosted copper, structurally controlled epigenetic montisotype, sediment-hosted lead zinc, commonly known as SEDEX, and I'll show you a couple of slides to hopefully convince you to stop calling them SEDEX. Broken hill types deposits with various interpretations of their genesis in relation to SEDEX, and I'll show you some information to make up your minds how much they are similar or different from normal sediment-hosted. And a bit of a left of field, separate kinds of phosphorites. And our focus was not on phosphorus, but on their rare earth concentrations. And in this presentation, I won't have time to say anything, so I'll just quickly bring up to your attention that some phosphorites are really strongly enriched in some rare earths, in particular some heavy rare earths, and they deserve a closer look. I will spend most of the time walking through the ICG family to a large extent because they are the most complicated ones. There is a fair bit of confusion still. So there is lots of confusion between deposit type classification and mineral system type classification, and there is just a great variety of them. So other deposit types are much more homogeneous internally, so I don't need to spend that much time. So within this family, in recent years, largely courtesy Louise Curie in Canada, she promotes the new name for them, metasematic iron calcic mineral system. And the reason being that some of the deposits affiliated with IOCGs, they're not iron oxide copper gold. Some of them are iron sulfide copper gold, and some of them have barely any iron oxide or otherwise at all. And some of them don't have any copper either. So call them IOCGs, that's a big stretch. And we have done the best we could to cover top down from the most significant to less significant. The most recent edition of courtesy One Cuthbert Group, thank you, Bruce, was Rocklands. And by now we have a very good coverage, certainly in the Cloncurry district. We're stepping out further west, but that's where our coverage is much more limited. But so far we have enough to base our work on. It's about good 1,500 samples. And we've done everything in the kitchen sink on geochemistry, and let's see what comes out of inter-deposit comparisons. So I'll start from where we started, from Ernest Henry, and Ernest Henry is a great deposit in Cloncurry, and to a large extent a great reason of confusion in the outside world what ICGs in Queensland are like, because it's by far the most studied and by far the most significant economically to date. There is a common misconception that everything is just like Ernest Henry, which is not the case, but still it deserves a very close examination. And I'll use example of Ernest Henry to illustrate our sample sampling selection logic and what we're going to do with the samples. So we have a large selection of drill holes covering different parts of the deposits and stepping out kilometers away. So we have a good chance to actually map out the deposit and the camp and probably go to a district scale, which is a very good opportunity, and that's something which we want to do more of. So on the basis of the available information about the deposit geology, we have a good understanding of the context of the drill course. As per usual, so we're doing routine drill core scanning so that we can easily identify different styles of alteration in bulk, and that guides our intelligent sample selection. And here we can see indicated the positions of individual samples. So there are in Ernest Henry that's about 200 samples, and is it enough to characterize the complexity and variability of mineralization alteration? Absolutely not. But it's just a simple fact. Well, we could blow all our budget on Ernest Henry, and that will be done. And that's not our job. Our job is to provide comparable data sets and comparable sample sets for, say, 30 deposits. So the properties of mineralization alteration in gross sense are well known. A few good PhD students did a fair bit of work. Rocklands is our newest edition, and we're going to review a couple of Rockland scores later today. So I'm going to use Rocklands as well to illustrate the workflow. Since we got a good representative drill course from the company who mines the deposits, and they know that it's representative. We have accepted the data to assess the context of the drill holes in the deposit geology. However, gives wonderful information to allow us to identify geological domains, major rock types, major alteration types, and on the basis of this information, we go and sample not blind, but we have specific targets in mind. So we can simplify the complexities which we see in notional 1-inch scale data into domains consistent with what geologists are doing in drill core logging. And you must have seen this information in your handouts for those of you who go for core viewing. So the intent is to simplify the information to allow you easy navigation through the drill core. And that's the same exercise we have to do to navigate the complexity of 20 deposits per year. So from the point of sample selection, the most important first thing we do is multi-element geochemistry. And this is a summary of everything we use. First of all, warning, so this is not advertising a specific laboratory, it's just the one we most commonly use. Other commercial laboratories have comparable services. We have done probably a much more extensive suite than any company would ever consider. Because as you can easily imagine, costs are very quickly adding up. But our purpose was to make sure that we have a complete characterization of geochemistry, including some non-traditional and difficult to digest and analyze elements. And highlighted here in red and orange are so the types of methods which we consider essential in general of a specific deposit types. Can't do without, and in orange, well, that's very good to have because that gives information about some elements which are essential for this deposit type. And as you can see, those of you who are using ALS, so these are exactly the same routine methods, particularly the ones highlighted blue on the left of the screen, which companies routinely use. So the basic outputs of geochemistry and what we can do with this to identify geochemical signatures of ore. First, this is the simplest illustration based on Ernest Henry by relative abundance compared to normalized to average crust. It can be normalized to anything else, it's just the simplest one to use the same normalization factor. And we can easily identify the geochemical signature by the order of relative enrichment top down. And so the first two elements, well, 3 elements which are consistent for all ICGs. This is the ICG signature is tellurium, copper, selenium for copper deposits. And beyond that, star diversity. So this very complex polymetallic signature of Ernest Henry is common to Ernest Henry and E1 and 1 or 2 other prospects. And everything else in the state, well, in this part of the world, is substantially different, and signatures are generally much simpler. With a more sophisticated way to explore geochemical signatures is by using something like principal component analysis. And so that's an interesting illustration of a relatively simple and consistent signature of Ernest Henry. So all the ore samples and the samples, the sizes of the symbols indicate copper grades. All ore samples from different parts of the deposits, they're fitting nicely in the same with the same association. So it's a pretty consistent geochemical signature through large parts of the deposits. Well, at least the parts of the deposits we had a chance to sample. Rocklands has a much simpler geochemical signature. You no longer see that complexity. You see the same telltale signs of ICG signatures in tellurium, selenium, but much simpler signatures are common for just about every other deposit, with a few exceptions. And Rockland's signature is a bit less consistent and uniform than Ernest Henry's, to a large extent because Rockland's is not one ore body but multiple ones, and so they have significant differences between them, and we can see it in geochemistry. So those of you who are going to the course talk, you'll be able to appreciate how different mineralization styles within the same deposit look like, and hence a bit of a diversity of signatures. Another newest addition to our recent geochemical investigations is Mount Dore, and shown here is the diverse and highly variable signature of this deposit. In many respects, Mount Dore is an exception. Similar to Ernest Henry, Ernest Henry is pretty unique in its signature, and Mount Dore is unique in another way. And so it's the only significant deposit with significant lead zinc, and also a fair bit of an addition of molybdenum and uranium, and a bit of excursion and a reminder that one part of Mount Dore is called Merlin, which is the highest grade uranium deposit on the planet. And a little bit more sophisticated way at looking at the geochemistry confirms that it's diverse geochemical signatures, and there is not one Mount Dore mineralization style. There are several, but sorting out these complexities is beyond the scope of these interdeposit comparisons. And placing a dozen deposits together, the main point of this couple of slides is to illustrate just how different, how diverse the signatures are, and how misguided is the question of what is the geochemical signature of ICG deposits in Cloncurry or in Mount Isa region. Well, which ICG? There are just too many of them, and this is just a difficulty of illustrating the complexity and diversity in 2D. So we're using 60 odd elements, and trying to reduce it to 2D does not give you a complete appreciation of the difference. And to appreciate it better, so just very simple manipulation of data visualization can highlight vast differences in geochemical signatures of different deposits. A unique position of Ernest Henry MB1, nothing is quite like that. A unique position of Mount Dore, quite well apart from anything else, and a reasonable diversity within the rest of the group. So it seems in this presentation that everything else falls in the same group. We can investigate it a bit further. And so this is the diagram which I have shown a couple of times, and I'm not getting again. This is a useful illustration that so we can group ICG and affiliated deposits in several distinct groups, and they have different geochemical signatures, different mineralogical signatures, and different economic potential so far. So ICG, so the Ernest Henry type, is the large one with K-spar magnetite dominant alteration. Everything else, with exception of Mount Dore and Calman, doesn't have much of a strong potassic alteration, and in the group with dominantly sodic calcic alteration with actinolite magnetite, lots of them are getting mined now. And the group in the green combines deposits with strong residual sodic alteration signature, and they're generally characterized by significant volume, but not great grades. So that's the group typified by Swan and Little Liver. And first, this is an illustration of the diversity of alteration styles in terms of alkali calcic and ferric alteration. So this diagram was introduced by Francois Montroy, Louis Correvo, and Eric Grunsky some good 10 years ago. It tries to show different metasemantic phases in the ICG and affiliated deposits. And the main point here is again diversity. Ernest Henry sits by itself in the top right corner, characterized by potassic feldspar and abundant ferric alteration. Mount Dore occupies a place on its own in the far left corner, and that's a very unique position. There are just a couple of deposits like that in this entire district, the ones we examined so far, and the vast majority sits in the bottom of the screen. Mostly in the field of calcic ferric to ferric alteration. This is, if you want to define a Cloncari style ICG, that's that at the bottom, the one which doesn't have volumetrically significant potassic alteration. You can find it, but you have to look for it. So the dominant signature is calcic ferric. A few words about critical minerals. There are several which are significantly enriched. The most consistent one is cobalt, which is common to a good half of all the deposits, and more significant ones, more significant concentrations are in Ernest Henry, Osborne, and Rocklands. And we can highlight here that a fair proportion of mineralization in those deposits are falling into the category of potentially recoverable byproducts cobalt. So cobalt is recovered in places at rates of 250, 200 and above. But the key here is not just the geochemical availability, but the mode of occurrence. And that's a little bit of a glimpse into more advanced analytical techniques. We're going into microanalytical characterization with a specific purpose of identifying the deportment of cobalt, the mode of occurrence. And here we can see for Rocklands that there are two main modes of occurrence in pyrite and in separate dedicated cobalt minerals. There are several of them present. And hence lies the problem of potential metallurgical recovery. So you need to remember about part of the cobalt in pyrite and part of the cobalt in separate minerals. Now we'll quickly depart from ICGs and into other mineral system types. The most significant one in the city of Mount Isa and in the western Mount Isa is so-called sediment-hosted copper. Well, the purists in the academic world would cringe calling them sediment-hosted copper, and to a large extent because they're not, well, they're hosted by sedimentary rocks, but they are late epigenetic deposits almost universally. And in most cases, we can easily identify their post-peak metamorphism formation. So quite often they're called Mount Isa type, and some people recently call them orogenic copper for that reason, to highlight their late structural time. So compared to ICGs, there is some diversity within this family, but it's not really as vast as for ICGs. Easier to see in the simpler spidergram manifestation. Here you can see that the dominant signature for ICGs, which is tellurium, selenium, it became much less significant. For elevated and common significance for elements like arsenic, antimony, and bismuth, and this is the common part of the signature. There is some diversity of signatures between Mount Isa copper and Capricorn copper and Lediani, Ledichelene, and Hill group. But as far as I'm concerned, these are geochemically they are variations of the same thing. And it's really remarkable how similar signatures of reasonably far away deposits, Lediani, Ledichelene group, and Hill, they are all but identical with a few exceptions. And in terms of critical mineral potential of them, so they have the common signature of elevated cobalt, and the level of enrichment is comparable to that in ICGs. And several deposits have a fair bit of their mineralization with the cobalt grades comparable to those which are getting recovered as a byproduct elsewhere. And a similar question and a similar problem for ICGs. It's not just about geochemical availability, but also the mode of occurrence. And similar to ICGs, cobalt is present both in carboniferous pyrite and 3 or 4 individual cobalt-bearing minerals. And to make it distinct and problem or interesting and more complicated compared to ICGs, there is a divergence between cobalt and copper mineralization in several deposits. So there are some parts of deposits which are very rich in cobalt. By very rich, I mean going to thousands of ppm, but having essentially no copper present. And in these cases, cobalt present is almost entirely as individual cobalt minerals. So it's in many cases you can mine copper and try and extract cobalt along the way, but so there are pretty substantial parts of cobalt on mineralization which are probably too low grade to mine for cobalt, and they don't contain copper to allow this to happen. So that's a bit of a complication. So now sediment hosted lead zinc deposits, and I'm starting from pretty images which show a distribution of key elements in the drill core. And for now, I'm trying to remind you why you shouldn't be calling them SEDEX, well, unless you understand it's a shorthand and they're not sedimentary excavated deposits. So if you look up from a sufficient distance, everything looks very sedimentary exfoliative, millimeter scale zoning, which is retained in strong folding. But having a closer look at some key, not particularly strongly mineralized samples, you can see some interesting features like in this image, green represents zinc sphalerite, blue represents dolomite, and you can see how quickly the layers of dolomite becomes layers of sphalerite on 9 millimeter scale. And we can see it even better when you take resolution from 30 micron of micro XRF to a few micron in SEM TEMA. And here you can see that razor sharp edge of texture preserving replacement of sphalerite replacing carbonates. And that's quite a common feature. And so this change here occurs at a range of tens of microns. Even though the individual layers can be traced for hundreds of meters, so this replacement can be traced to a few tens of microns. So it's a beautiful example of texture preserving carbon replacement. Geochemically, it's interesting. I don't have time to say much about broken field types. It's a wonderful conundrum and discussions over the past several decades, which probably will continue for some time, whether broken field types are just metamorphosed SEDEXs or not. Not buying into that debate. I'm just simply showing the geochemical signatures, and worthwhile to note significant differences between the two. So highlighted in red boxes are the areas where the differences are most significant. So the sediment-hosted, proper sediment-hosted lead zinc deposits have strong signatures of elements like thallium and mercury. Thallium in particular, it goes into tens to sometimes hundreds of ppm, and it's a well-known feature of them for the past 20 years. And broken field types, they just don't have thallium. And they have a fair bit lower amount of mercury. And the second box highlights the area with the element which people don't normally pay attention to. And it's europium. So it's not super significantly enriched, but that uptick which is present in broken field types is quite symptomatic, and you will see a few slides later its significance. That's actually a quite typical feature in both whole rock geochemistry in ore samples and in mineral chemistry. This positive europium anomaly, which is quite unique to broken field type deposits. And a little bit of local controversy. I was just playing with this the night before. There is a broken hill type deposits. There are sediment hosted. Let's just display them on the same discrimination diagram. And put in the mix some deposits which is often left out and overlooked. It's not quite well. It's not in the western succession. It's not together with broken hill types, Dugud River. Here you can clearly see that there are well-defined domains of sediment-hosted deposits, well-defined domain of broken hill types. They're nowhere near each other in their bulk chemical compositions. And Dugud River chemistry sits neatly in the middle, starting from the outskirts of sediment-hosted and getting intermingled with the signature of broken hill types. And that's a confirmation that Dugud River is complicated. And if Nick Duriv could be here today, he would confirm that. And there is a poster just out there with a PhD student trying to figure out the genesis and geology of Dugud River. And so this geochemical discrimination diagram confirms it's complicated. It does look like a geochemical hybrid sitting halfway between sediment-hosted lead zincs of the western successions and broken hill types, a little bit closer to broken hill types. This is the only slide I'm going to show on Northeast Queensland. So we started with Northeast FA a bit later. We started from tin tungsten deposits. We've done an FA bit of impression on those. We expanded into other granites associated deposit types and looking at critical minerals like indium. So that's the complexity and summary results from Northeast is a topic for another conversation. So on top of our own work, just routine characterization, which is getting less and less routine as we're getting into microanalytical techniques, we're doing a very large volume of work with external researchers, external organizations. I don't have time to dwell on much on that, but literally we're talking about dozens of projects using university research students, postdocs, and well-established researchers like Professor Al Martha from the United States, Professor Maverick Jeans and his students and postdocs in NU. And I will just show you a few teaser summary results from some of them, and Elena will get into some more details. So this is our very own results, and remember about European positive anomaly in chloride geochemistry. This is much more prominent looking at apatite chemistry, and this is our very own results looking at apatite. So this positive European anomaly we have seen only in broken hill. And here we show results for Moronon. So the pattern is essentially the same for Canada. Several years ago, we started our adventure into using stable metal isotopes for mineral exploration. It's largely spearheaded by Ryan Mather and students working with him. So these are the results of using metal isotopes in magnetites in Ernest Henry. And this is results of a published paper of a PhD student. And so the main conclusion of this study is that using stable isotopes of iron, titanium, of oxygen, we can clearly see, for example, that there is no way the fluids producing magnetite could be derived entirely from magmatic sources. So there is a magmatic component, but the signature is mostly non-magmatic, mostly verging towards based on brines, which is consistent with many hypotheses hypothesizing the presence of based on brines or their derivatives and their own formation of ICGs. In more recent times, we started doing a fair bit of copper and zinc, copper and zinc minerals. There was the first study which was finished on Mount Isa copper, so these results are published. And since then, we have done massive campaigns of sampling and isotopic characterization of chalcopyrites and pyrites and magnetites all over Northwest Queensland. covering the large amount of ICG and affiliated deposits, and some first results are shown here. And also on the slides on the right, showing the version of the slides Joe showed yesterday, the applications of metal isotopes to exploration in hydrogeochemistry. And these are components of the same studies trying to investigate potential uses of something which many people, most people in exploration never think about. And I didn't know that we were iron isotopes, and why should I care? And by now I'm a believer, so we're doing more work to make it worthwhile. And as far as I'm aware, so we're doing more work on this than all the other state surveys in Australia combined. So some of these results are going to come out in the next probably 6 to 9 months. Another bit of a teaser of the use of mineral chemistry for mineral system characterization. These are results of a PhD student from ANU. He's finishing his PhD research. The focus here was on mineral chemistry of spheroids, and on this simple two-dimensional diagram, we can clearly see how we can differentiate different mineral system types based on chemistry of just one mineral, looking at just two elements. So that's pretty remarkable outcome in its simplicity. In most cases, life is not that easy, not that fair. But this is an indication of the uses of something which is normally the realm of academics, and how it can be useful for exploration, how you can easily identify early on which system produced spheroid. And now, very quickly, just in a couple of slides, an illustration about one of the biggest end games of this whole exercise, how to take the work done on deposits and expand it to distal footprints. So in places like Ernest Henry, so we spent the longest time there. We're reasonably comfortable that we can navigate our way and recognize proximal signatures within 1 kilometer along proper structures. And so we are somewhat struggling to go beyond 1 kilometer in whole rock methods, and we're going many kilometers. Probably the whole rock geochemistry and mineralogy is just not sensitive enough, and we need to use something else. And that's what we started doing first with our friends in Codes. That was, to my knowledge, the first dedicated project trying to use mineral chemistry by identifying distal footprints of ICG deposits. That was concluded several years ago, and now we continue this work on our own. So the intent is to take the outcomes of the Code study from a few years ago, use the learnings to do more and better, and build up the data set and knowledge, helping us to navigate further away from the deposits into hundreds to meters to kilometers, and take it from deposit scale to chem scale, and ideally in the glorious future, which is probably going to be to 2025 and beyond, to take it all the way to places like E1. But that's much more complicated, and the entire concept is to start from the inside, from the known, and do baby steps for as long as we can to find our way around. There is a fair bit of the data which has been released, and I'm very keen to hear from you, well, whether you're aware and how useful you find the data. So far we focused mostly on releasing data without any interpretations, just to make it more easily accessible, and much more is going to come in the next 3 to 6 months. So one of the important points of our work is to disseminate results in meetings like this, because quite often it's much more conducive to have a face-to-face conversation than to write a paper for 6 months and hope that the right people would read it. And so we're going to do more of these events. And all of this could only happen with the help of multitudes of external people, external organizations, and in particular people present here. Some are absent, representatives of the companies. So you see it's a very busy slide, and these are most of the companies who did significant contributions to the study, and I can make more space on the slides only for a few more companies, and a few more already contributing, and we're going to pass to a few more of you. Please help us with access to a drill course, particularly all those boring barren holes in the middle of nowhere with barren magnetites. We just want to see and work on this. And this is well and truly all I have to say in the time available. Thank you very much, and please give your feedback. Thanks.
Questions for Vlad? Great, thanks again, Vlad. The next presenter this morning is a key member of Vlad's team, Elena Belousova, and she'll be giving a presentation Advanced Analytical Techniques to Assist Mineral Exploration. Welcome, Elena.
Thank you, Evan, for introduction. Well, good morning, everyone. So today I am going to talk about analytical techniques we're using, including some advanced analytical techniques. And these analytical techniques help our work to characterize the main mineralization system. So we really hope this new data set, quite complex data set, will really help to give you some detailed characterization on the mineralogy, on the isotopic and geochemical characterization of this mineral system, and also their footprints. Well, you've seen these maps probably several times. I'm not going to dwell on them very long, but these maps just to give you appreciation how diverse the different mineral systems are across the state. So we have mainly the mineralization and deposit associated with felsic magmatism in northeast Queensland, and very contrasting in different and also diverse deposits in the northwest Queensland. So this is just to emphasize that we're trying to build up our workflow to make sure we just collect a very consistent and uniform data sets across range of these deposit types and also across the different geographical locations. So what is our workflow? Obviously, we already talked about it several times. So we starting with our core scanning, and several people emphasize the different targeted compliance we have with Mineralizer, Syro Petrophysics Lab. But I would like to just emphasize that we are very lucky to have our own high logger instrument. It's our main working horse, and we most of our drill course coming through this instrument before we starting our detailed sampling for the whole rock geochemistry, and also for this expensive and quite detailed exercise to look at the microanalytical samples. Just to emphasize, you've seen already some of this data. This is the high logger data for the rocklands, and it's not only because it's a beautiful example of the high logger data, but it's also something we are going to see this afternoon. So in the preparation for this workshop, we just emphasize importance of this data again. So you can see here how clearly we can define different mineralogical domains in this drill core. And this is really ensure that we have a very representative sampling, not only of the main ore intervals, but also the host rocks, and importantly, all the alteration that we see here. For example, we have extensive area of the actinolite, albite, also the block of the where we see the carbonate, quite a big zone. But also, it's without this sort of data, it's really would be easy to miss some small interval with K-feldspar alteration. So I can't emphasize enough how important these scanning steps, first high logger data for our further analytical work. And what is very pleasing when we compare the different data sets, in this case, the data coming from Mineralizer in comparison to our high logger data. So we have here distribution of iron, silica, and titanium zirconium ratio, which are very contrasting and correlates quite nicely with these domains which we define with high logger. And this is also consistent with our visual observation during the core logging. So you will see this this interval of the dolomite, siltstone, and the carbonate zones during this afternoon. And obviously, Mineralizer is a better instrument just to pinpoint where the main mineralization is. It's often quite obvious in hand specimens, but Mineralizer data, together with data provided by industry with their assays, really ensure that we don't miss not only the main mineralization interval, but some minor interval or intervals where, for example, copper and cobalt are decoupled, and it's so easy to miss it unless we have this precious information and data. Well, some of the spidergram and whole rock data, and honestly, I'm not going to dwell here for too long because Vlad did quite a good overview of the importance of our characterization and using the whole rock data to discriminate different type of deposits, but mainly just to point out that the range of the elements we're analyzing and the different methods. So we try to use the methods which are commonly used by industry, so you have something to link to your data, but also we're using the range of the very specific analytical method available at ALS, just to make sure the data is the most precise and give us the best information we can do. So when I look at this recent data set we collected, you can see I counted over 20 different ALS methods in these data sets. So this data will be available very soon. We already put it together. It's in a process of being released. Well, now I will be probably focusing the rest of my talk on our microanalytical work and microanalytical studies, just to show you why we're using this technique, how it's important, and what implication it can make for your work, guys. So we use quite an extensive range of these advanced analytical techniques and how we can make it happen. We have a relatively small team. Most of us are present here. So of course, we are unable to do it without the contribution from our numerous collaborators, CSIRO, AXT, range of universities, and all the postdoc and PhD work and projects we have. And it's not only give us access to the analytical equipment, it gives us access to expertise and knowledge, not only to collect this data, but to get a right interpretation on this data. We're also very proud to have our own Tornado instrument, which was installed last year. And Alkis and Tamini are the super users, so they look after this instrument and ensure we run this instrument daily. So Tornado now is used in the routine of sampling work. So when we're sampling, the instrument is situated also at EDC. So if we have any questions we can't resolve looking at the core, what sort of mineral it is, we can do, the instrument is perfect for the spot analysis. We can do spot analysis straight away, very quickly. And the instrument doesn't need a lot of preparation. So we do the light polishing and we set up this instrument for overnight run to create this sort of maps. So this is an example, the pigment sample where we can see a distribution of individual elements. You probably can't quite see it. This projector doesn't give all this benefit of the imaging, but I hope you will see, you will have a hard copy and some of this data will be published. So you will be able to appreciate the details of this scanning much better. So the sample size here, we can fit up, you can see dimension up to 19 centimeters samples, and we can have this mapping done for the selected samples. And you can see from July last year, we have done over 120 samples. I look at the record and I think it's quite a correct estimation of the extent of the work we've done using this instrument. Again, the example from the rocklands, you can see here the sample, just our sample, we just take a usual photo, and then we can, with tornado instrument, we can produce maps for individual elements or several elements. So in this case, we look at the distribution of sulfur, copper, and cobalt. And what's interesting here, you can see a lot of, if you can, some bright blue spots where cobalt actually sitting not within the pyrite, but form individual clusters. This instrument is also enable us to get these AMIX maps for the distribution of the different mineral phases. Very useful, particularly on this scale, you know, when you take, you know, half of the core and have this information available. Another work Vlad already emphasized, the detail work we can get, and these detail maps, which we can get from the Maya Mapper instrument. And this is more powerful. It's a high intensity XRF instrument where we can have a resolution on the very fine details. And again, this example, what Vlad already showed on a sample from the lead zinc, Mount Isa lead zinc deposit, where you can clearly see, hopefully here, this green bands is representing the zinc, and that carbonate, it was replaced by sphalerite. So this sort of data and images really enable us to clarify the models for the deposit formation. And as well as this instrument allow us to map much larger samples, up to 30 centimeters, and this high intensity, it's capable to detect the tiniest particles and distribution of such element like gold or silver. And this little example just to show you when we ask the question of the distribution of silver, and for example, in pigment, you can see these light blue circles. This is specks of silver, which are mostly associated with galena, but in some case is sphalerite. Well, another instrument we started to use a couple of years ago and can't get enough. This is the TIMA instrument. So TIMA stands for TESCAM Integrated Mineral Analyzer. So we do a lot of TIMA mapping with our collaborator AXT, and Elisa is here representing this. We do it with the Curtin University, but a bulk of the analytical work done at the labs at the QUT. And we are lucky because QUT labs located just 200 meters away from our main office. So our staff was trained to use this instrument. So we come in and collecting data ourselves and processing the data ourselves. So we're using quite a detailed resolution. You can see on this slide, we're using the dot mapping using 2 microns pixel size. Why we do it, this detail work? Look, if we use this standard 2.5 millimeters grain mounts, it takes us sometimes up to 6-8 hours. So in the next few slides, I will show you why this fine resolution is important and why we spend this time. But also justify to say we're using Friday session, which enable us to load the cell and get, 7 samples, run quietly over weekend while we are having our good time away. So, yeah, so this is the TIMA instrument. And just to show you the beauty of the data output we're getting from this instrument. So you can see very high resolution backscattered electron maps. Then you can see the elemental distribution maps. So we can create any, sort of maps for individual element or for the group of elements. And this is a beautiful example. I love this slide, this thin section from pigment, where you can see these bands of the apatite and sphalerite, which are very brightly shown in this green color of apatite on the elemental maps. So it gives you not only the understanding of the distribution of the different minerals, but there, for example, intimate relationship between the apatite and sphalerite in this granular garnet, which is bright red on our face map. I want to move from this slide. What's going on? Somehow we stuck on this slide. Please help. Okay, is this, no, it's too far. Let's try and get one before. Okay. Well, another interesting map, TIMA map. So this is the sample from Dougal River, and we have a poster back there showing a lot of information on Dougal River. But I thought this TIMA map is very, very good example where we can resolve the mineral cross-cutting relationship and also mineral paragenetic relationship. And sometimes we struggle with, you look at the hand specimen, you struggle to see what comes first. And actually, this makes your life a bit easier. You can clearly see this pervasive albitization of a print in the host rock, and it's clearly cross-cut by a later potassic alteration. These hot pink colors, representing this. And the latest event is cross-cutting veins with carbonate in dark blue and gray quartz. So in this case, you have a very clear and very convincing example of this cross-cutting relationship. Another benefit of the TIMA instrument that we can produce these maps with individual mineral faces overexposed of the backscattered images. So you notice we have so many different collaborators in different universities. So when we send, to people who looking at the individual minerals and try to zap them and target them with the laser, this is the best, material. You can send the sample, you can send this map, so the student doesn't waste time looking for these minerals and in their samples. So I would like just to show some examples of this detailed work which we do in situ, work which we do on some of the minerals. So just to make sure you don't fall asleep, I will break it with different, contrasting stories. And I would like to start with apatite because it's my old baby. I just did a lot of work when I was a PhD student on trace elements on apatites. So this is our first results. We did ourselves with QET labs to collect the trace element and first initial uranium-lead data on the apatites. And Vlad already stole my best diagram. So we've done this work on appetites from Maronan, Mount Dore, and Rocklands as the first run. And you can see this red flag for the Maronan. I've collected thousands of analysis for appetites from the range of igneous rock types, and I've never seen positive europium anomaly. So we can discuss nature of this positive europium anomaly, why it happened later on. We have some ideas, but if you have more, we'll be happy to discuss. But what is important here, that this anomaly, that's exactly what we see if we look at the whole rock data. This is one of the signature of Broken Hill type of deposits. So we can use a single mineral, and you can just go and pan it and get your appetite. And if you see this positive europium anomaly, here you are, you're on the spot. But what I want to show also, that in spite of this distinct, trace element patterns, we see quite a diversity and quite a range in the rare earth element composition in this case. And if you look at some other trace elements, probably hard to see here, but just to emphasize, even the appetite from a single deposit is clustering in the individual class. So that's why when we do this sampling, we need to have quite a good understanding where the sample came and, what area we analyze and what the paragenetic relationship of these appetites. So again, we're going back to Rocklands, where we have a very nice range of the different breccia types, but also we have a sample which is we took from the host dolerite. So, and if we just look at the trace element data appetites from these 6 samples, you can see a significant difference in the amount of rare earths in the appetites, but also a subtle difference in the trace rare earth patterns. So without this detailed work which did on a TEMA, the interpretation of this data will be not as trivial. So here I just wanted to emphasize, we see in appetite from dolerite, we see rare earth element patterns very similar for appetites from igneous rocks. But in contrast, if you look at appetite associated or within the garnet, you can see the quite significant depletion in heavy rare earths, because we're competing with garnet for heavy rare earths, and obviously appetite losing this competition. Another distinct patterns in appetites are related to this very late quartz carbonate veins. So all this TEMA image make this interpretation, it's much more comprehensive. Also, if you look at the other trace elements, here we have quite a few fields, and you can look in details later on. This is the fields I use from my PhD work, where I try to discriminate appetites from the range of the igneous rock types, but also I plotted appetites from the granitic suits in the Mount Isa region, just grouping them is in the reduced, from strongly reduced to strongly oxidized towards the right side of this diagram. What is interesting, the rocklands sitting very tightly in this reduced end. But if you look, some of these appetites have quite a significant amount of the iron. And then again, if you're coming back to look at the TEMA images, this is specific appetites which are in a paragenetic relationship with the actinolite, magnetite. So it's reflecting this crystallization environment where the iron is abundant. We also try and get the uranium-lead dating on the rocklands appetite. And if you look at the all the samples together, it's quite a mess. So you can try and get a couple of the regression lines, and good luck to justify, is it a good, justify regression line or not. And this is coming much easier and more convincing if you look at the individual apatite population and know where they come from. And what is interesting, don't quote me yet because it's just very initial results, but it looks like that apatite which is sitting in our altered host rock dolerite, and those which are locked within the garnets, they given quite older age, around 15-30 million years, but apatites which is within the breccia and associated with actinolite and magnetite, given a slightly younger ages. So we tried to resolve this data and I'll give you a better answer. Mainly because rocklands provide us with the paradise for geochronology. So here we have a map where we show the range of the minerals we can use for uranium-lead dating. So we have apatites we have these bright yellow crystals. This is titanites, we have zircons, and we have rutiles. And in the image which show the major mineral phases, you can see this huge biotites, iron-rich biotites, annite, which is associated with these sulfide veins. So we can use these minerals, and we can actually zoom in, look at the individual grains, micro inclusions we have, and we can target that probably in the next round for our geochronological work. Another good example that this particular sample, single sample, give us a possibility to date different minerals and different radiogenic systematics, which can, in the case of rocklands, provide us the timing of relatively cool hydrothermal events recorded in biotites, for example, in rubidium strontium systematic, to much higher temperatures in apatites, and apatite, for example, lutetium hafnium systematic, even higher, and finally in the igneous range of temperature for zircons. So this is our future plan for this particular deposit. Well, if you had enough of apatite, I would like to switch to another story. And this is the story was very complex for me because I never had anything to do with stable isotopes. So I try to give you, my best understanding I could. So we received this data just a few weeks ago. And I tell you, the first shock was, it's a single deposit, several samples, and look at the range in sulfur isotope delta 34. It's very comparable with the general terrestrial range. So, first shock, but let's look at the TEMA image again. In TEMA image, when we look at it, we saw that quite a few cross-cutting veins, and we thought maybe this complexity is because we have different population of the sulfides coming with these different waning. All of them have quite a nice range of sulfides. We have chalcopyrite, pyrite, chalcocite, and bornite. So let's look at even one main vein in the single deposit. This is sample from the mammoth, and we can see here a range of the delta sulfur 34 from minus 16 to over 20 units. So even the single, sample and single vein give you this huge range. So it looks like there is nothing simple in Mount Isa. There is nothing simple analysis. You can, get your data and have a straightforward interpretation. So let's look what we have and try to break this data and give some sensible explanation. First observation, we can see that the greenstone and mammoth are characterized by light isotopes sitting in this negative field, while the Pluto Esperanza have the much heavier sulfur isotope signatures. And this is consistent from their host rock types. So when the first group sitting hosted by quartzite, the second one is in the black shale and siltstone. Is it significant for this sort of sulfur isotope distribution? Then let's look at the literature data and see what sulfur isotope is signatures for some geological reservoir. So if you look at the sulfur isotope for the magmatic range or hydrothermal, and I try to put it the red bands here, which looks like a bit purple, but you can see them. So you probably can say that greenstone and mammoth have some contribution of from the magmatic or hydrothermal sources, but you can't, you probably can hardly say it has any significant role in Esperanza. So what is responsible to drive these sulfur isotopes to this light isotopic end? And most literature agrees that you have the sulfide reduction bacteria, which in this processing take the sulfide and produce the this lighter isotopic signature in pyrites, mainly because the bacteria prefers lighter isotopes. So that may explain this negative isotope signature in the greenstone. But if we look at the Esperanza and this extremely heavy sulfur isotopes, what processes can explain this isotopic signature? And literature indicate you need the marine evaporites sulfide, where the bacteria sitting in closed environment, and it's create this residual sulfide, which is this time getting heavier and heavier and produce this heavy sulfur isotope signature. Well, we also did a comparison with the data available in the literature. So we compared the Esperanza with the Mount Isa copper, and actually they are very comparable sulfur isotope data, and which very encouraging, they sitting in a similar lithology. While the mammoth, we had a direct comparison with the data coming from the PhD work. So we're quite happy that the data is there. It's just interpretation and processes which are involved into these different, processes of the sulfur fractionation are very complex. In the next steps, we probably would like to see if the sources for sulfur for Capricorn copper are similar for the sources for the copper isotopes, and also to try to help to discriminate different sulfide population. The next step would be the trace element work on these sulfides. A little bit to overlap with Vlad's story on the cobalt deportment. Again, I'm showing this TIMA image, again and again emphasizing that our time spent on a fine resolution is not wasted. So here, unfortunately, I can see they have tried to look. There's some tiny micron scale inclusion of the cobalt mineral in this pyrite. So it tells us that cobalt in pyrite not incorporated in a lattice, but it forms its own mineral. So how significant it for cobalt extraction and recovery? It's just for industry to think about, but this is the information. And also another example, Vlad showed before, just again to emphasize, in this case, we have this huge pyrite grain shown in yellow, and we have a quite large grains of the corallite, mainly shown in this very light greenish yellow color. So again, in this case, cobalt is not associated with pyrite. It's closest sits with as its own mineral. And just to verify this observation, we did the laser ICP-MS map on exactly the same area we did our map, just to verify that our finding and identification of the minerals are correct. And you can see this high signals and counts per second for cobalt really correlates nicely with the site where we have this cobalt containing minerals. This laser mapping is also very good because we can compare different critical and rare elements, how they behave. And you can see that cobalt here correlates nicely with copper, but also with bismuth and antimony. In contrast, the thallium, for example, it's preferred to sit in pyrite. And you can see this nice correlation with iron and sulfur in this case. So this sort of, work gives us, quite a fine details, but I think it's important for the cobalt story, for example, or other critical minerals, where they sit in, how they distributed in our minerals and deposits and in all. So all these very detailed mapping and we're doing over several years now give enough samples and detailed information so we can provide it to our collaborators, particularly doing their postdoc or PhD research. And I just listed some of these current and previous PhD work which was done and driven by GSQ project and done on our samples. Just a few examples, and Vlad already mentioned interesting outcome of Chris Ignis' work on sphalerite, and this very busy slide, but it shows just the range of the elements he explored in sphalerite and also the range of the deposits in northeast and northwest Queensland. And the same diagram they used to show the distribution of cadmium versus iron, very simple, straightforward, and we see this clustering of the data with the deposits of set-hosted deposits versus IOCGs and Broken Hill type. So for the Broken Hill, for example, now you have at least 2 different indicator minerals to use for your exploration. Another tiny example is the work by Xin Wan, and we provided her samples and these details maps for her work to explore apatite, garnets, and calcite. And this initial data, TIMA data, provides her very good, understanding on the paragenic relationship of these minerals with the other mineral phases. And outcomes come quite nicely. So the different ore stages and different mineral paragenesis of these minerals produce quite a distinct populations. For example, you can see the apatite and its contrasting rare earth patterns in the ore stages. You can see 2 distinct populations in the garnet and also calcite associated with ore and late calcite. So it's a very nice outcome. And when Xin started to produce her uranium-lead ages on apatites, it's amazing correlation where you can see the older ages are found for apatites within the garnets, and the youngest, which are logically associated with these carbonates and quartz in the later stages. And what is significance of outcome of this sort of work? It helps us to refine the models and the phylogenetic relationship of the, for example, in this case, for Ernest Henry. So where previously appetite was, considered as in an early stage, but now we can see quite clear evidence that appetites have quite a few population just across the different stages of this mineral system. Well, and just to summarize what we have, I just put together the map. Probably doesn't justify, but I probably can more emphasize the table where I listed some deposits in this list and subdivide them by deposit type. So we've done just a lot of work on over 50 different deposits in Northwest. Some of those deposits are listed there. All of them were high low. Most of them have whole rock geochemical data, and you can see numbers for our microanalytical works in the last 3 columns. So if you see your deposit in your list and you never seen the data, please talk to us. We will share with the data. Or if you have your deposits, your drill core, where you think you can use our approach, our method to resolve your questions, please talk to us. We will be happy to work on your drill core, on your samples, and help you to answer your questions. So hopefully all this data, all this information will be great addition to understand, this geochemical and mineralogical signatures of ore deposit. It will be helpful for the vectoring, for the distinguishing the sources, to resolve the different type of the deposits, and identify the better geochemical vectoring. So as a whole, as a pre-competitive data, we really hope this provides you some good ground for your successful exploration. And last but not least, acknowledgement to our team members, because all of us contributed to this work, and not only us, but our external collaborators, and some of them listed here. So thank you so much. Probably finish on this one. Thank you.